This webcast continues the review of the unbalanced force model, and I have reached problem 5. So in this problem, we have a shopping cart. It's initially moving at a speed of 7 meters per second, but it slows to a stop at a constant rate of acceleration. While it is stopping, it moves 10 meters across the parking lot. What is the net force acting on the cart? So this sounds very much like a situation where I need to use a kinematic equation, because they're giving me things like the displacement and the initial and final velocity. I'm going to make a list of the things that I know. Now I know the mass of the cart is 31 kilograms. Its initial velocity is 7 meters per second. It slows to a stop, so the final velocity is 0. And as it's moving, it has a displacement of 10 meters. Okay, I'm looking for the net force. Okay, well, Newton's second law, if I wanted to find the net force, I would need to know both the mass and the acceleration. I know the mass, but I don't yet have the acceleration, so that is something that I need to find. Remember, acceleration is the connection, the linkage between Newton's second law and these kinematic equations. Okay, so I think I need to find acceleration first, and I need an equation that involves VI, VF, delta x, and A. So that reminds me of the third equation. VF squared equals VI squared plus 2 times the acceleration times the displacement. In this case, the thing I'm going to solve for is the acceleration. So the acceleration would be VF squared minus VI squared divided by 2 times the displacement. Let's see. Uh-oh, I almost plugged in the wrong number there. The initial velocity was 7. The displacement is 10. And so let's see here. If you notice, there's nothing canceling my negative sign, so I'm going to get a negative acceleration. That's frequently the case when something is slowing down. And so I get negative 2.45 meters per second squared. That's the acceleration. Now that I know the acceleration, and since I already knew the mass, I can use Newton's second law that says the net force equals the mass multiplied by the acceleration. So I have a 31 kilograms. The acceleration is negative 0.245. And so that net force is going to be a negative 75.95 newtons. It's probably negative because it's opposing the motion, right? If we thought about the force diagram on this cart, the weight and the normal force are balancing in the vertical direction. There's no applied force in the direction it's moving, but there is friction. So that net force is probably this friction force. But anyway, they didn't ask us to figure that out. Let's go on to the next page, the last page here, where there are some questions that are fairly conceptual. So the first one is, what is the essence of this? Oh, and this should say unbalanced. Or net force model. And it says draw the figure and give a brief explanation. Well, the figure that we had, I remember it had these two, this little diagram. And on the left-hand side it said, if the object is accelerating, and accelerating means either the speed or the direction or both are changing, right? Well, that means that the net force is not equal to zero. In other words, there are unbalanced forces acting on the object. So if you know the left-hand side, you can infer that the right-hand side is true, and vice versa. If you look at all of the forces on the object and you find out that they do not add up to zero, then you can deduce that the left-hand side is true. The object is going to be accelerating. Okay, so an unbalanced force causes acceleration. That's the essence of the unbalanced force model. Okay, let's look at some of the true-false statements. We'll decide if the statement is true and say so, and if it is false, we want to make a modification to make it read as a true statement. So the first one says, if an object is moving at a constant speed in a straight line, there must be no forces applied to it. Well, I know that's not true because in many cases we have talked about a situation where, an object is moving at a constant velocity and there have been all of these forces acting on it, right? So if the normal force is balancing the gravitational force, if the friction force is balancing the applied force, this is just one example. Well, the net force is zero, and it's moving at constant velocity. But that is obviously a case where there are some forces applied, and yet it is moving at a constant speed in a straight line. So this is false. Let me just say that, and let's make a change to the statement here. It's not that there are no forces, it's that there are no unbalanced forces, right? There can be a lot of forces acting on the object as long as the net force in both the horizontal and vertical direction are zero. Okay, let's look at the next one. Objects at equilibrium are always at rest. Well, see, I know that's not true because I drew that example in part A. That would be equilibrium, right? So objects in equilibrium are either, like at rest is one possibility, but there are two scenarios for equilibrium. So objects at equilibrium are either at rest or moving at a constant velocity. Those are the two scenarios for when net force is equal to zero. Okay? C, this statement is an object always speeds up in the direction of the net force. At first glance, that seems pretty good. I could think of, I have a truck speeding up. And so if the applied force, let me get my little forces in here first. If the net force would be the applied force minus the friction force. So if the applied force is greater than the friction force, then the truck speeds up. and that's because we have it moving to the right. We have the acceleration in the direction of the net force to the right. That means when velocity and acceleration point in the same direction, the thing is speeding up. Okay, but is that true in every situation? What about the grocery cart? You know, the problem we just did. There we had only one force in the horizontal direction. It was friction. So here there are unbalanced forces, right? The acceleration is to the left, even though the cart is moving to the right, and so it is slowing down. So acceleration is always in the direction of the net force, but that does not mean that it's always speeding up in the direction of the net force. So instead of saying speeds up, I would cross those words out and put accelerates. The direction of the acceleration is always the same as the direction of the net force. And then the last statement down here, the two forces that make up an action-reaction pair always act on different objects. This action-reaction pair, that's like a Newton's third law pair. That's what it's referring to. And yes, I think that's true, right? Because we said that it has to have the same type of force, and the only difference, so if we had object A and object B interacting, the force on object A by object B would be the same amount, but in the opposite direction. That's why I'm going to put that negative sign there, as the applied force on object B by object A. This is an action-reaction pair, or a Newton's third law pair. And to see this, you know, one of the forces in this pair is acting on object A, but the other force in this pair is acting on object B. So I think this is a true statement.